Hello, this is my presentation for my project number 5 for my math course of Calculus 3, an elusive integral. Alright, so for our project here, we were discussing this integral. And we were trying to figure out how we got the answer to this said integral. And this integral, obviously here, is an improper integral due to the nature of what its range is supposed to be on the integration. As we're trying to express a value over an infinite range, which, is something that's almost pretty much incomprehensible. So I'm going to discuss how I managed to figure it out, and how I figured out each step along the way. So the first thing I did, basically, I wanted to understand this theorem. So I did some very rough readings without writing anything down first to have a general idea, not taint my brain exactly on exactly what needed to be done and how it all worked. I still wanted to make an attempt after the short stint of research to solve the equation, which honestly I feel like I still couldn't get very far because I'm still trying to comprehend the whole concept of applying double integration to a improper integral. So first, I started with our teacher's mentioning of solving this equation with a straightforward result using the concepts of double integration and polar coordinates. That's what he mentioned in the description for our project. So I went ahead and looked up the Gaussian theorem, the Gaussian integral, and I found the Wikipedia page, and the first thing to come up was actually the exact method that our professor suggested we use. So this provided me with a little more detail, but I didn't exactly want to use that as my answer. I wanted to make a few mistakes and compare, so I just looked at the various steps and tried to find some clues as to what would make the proper solution more viable. So I could basically add more pieces, find more pieces that I could add to the full jigsaw puzzle that is the total solution. So first I went on YouTube and continuously watched bits and pieces of videos until I found an example that didn't solve the problem but gave me a rough idea to solve it. So basically, the first thing that really confused me was how did we get it to go from a single integral to a double integral? So when I went onto YouTube and I found a couple videos, and I will add the links of these videos, I first found the video by a guy named Mike the Mathematician, and he was using Fubini's theorem, which is what we mentioned in 5.2 and 5.3, was using Fubini's theorem to solve things. And it's kind of weird because it seems like there's so many different, it's a very vague methodology to use Fubini's theorem. I look at it and I see that what we're kind of doing is we're figuring out how to we're just creating a double integral. So it's like computing a double integral by integrating in one variable at a time. So I know it's basically like slicing something up into multiple pieces, but it was kind of weird because all the videos I found had a very different approach. There were all these different improper integrals, and one of them, we had one, before I show you the full method here, we had one that did this, that basically took the infinite to 0 of it took the concepts of E and turned them infinite, or didn't turn them infinite, but it basically took it kind of created it didn't work, because what it did was it kept basically every formula or every improper integral that was in the video had an x and a y in it already. So it was pretty easy to expand on the concept of Fubini's theorem, because I feel like it was the pieces to do the double integral were already there. What blew my mind about this, for specifically for this integral that we're doing, was that somebody, like in the Wikipedia page, it does kind of discuss it. It shows you that that's like the first step is turning it into a second integral. And I'm like, but I was like confused. I'm like, where does that come from? And then there was a video that explained it further, and it was by Dr. Trevor Brazett. And basically what it did was he converted the entire thing into I, right? And then he squared it. So he squared the entire thing, so he multiplied it by itself, right? So that's what happens, is it became multiplied by itself. And then he was able to take one of them and convert the other to the variable y instead of the variable x. And because of that, it became basically a solvable double integral, right? So then what did he do? Well, pretty much at that point, the entire thing was pretty easy to go for after that. I kind of watched that video and like double checked with like the Wikipedia page too, just to see if it had similar ideas. Basically, I tried to figure out why, but before we go into the concept of the whole going into it with Jacobian and all that stuff as a double integral, which we've already been doing for our homework and stuff for 5.3, I wanted to understand. The other thing I wanted to understand and break up on was, why do we do this? Why did we get it into y? And like, how did we even come up with the idea of putting in the second variable y? And we did so just because there doesn't seem to be like really any explanation for this idea. It's more like a concept, but it kind of reminds me of how we use like simple tricks of multiplying each side in a function, or when we find a perfect square, just applied to a more deeper level in the realm of calculus. And when we assign that idea, we assign it to Fubini's theorem. So then basically it's kind of like a mix of Fubini's theorem and then all these little extra tricks that we learn in previous lower levels of mathematics. So now that we have the integral as an x and y, we multiply them together and did all that, it becomes r. We can turn it into r with the Jacobians, with Jacobian theorems, and so we get that. And so basically what we can do is we can convert the e times the e to the negative x squared times e to the negative y squared, and just make that e to the negative x squared plus y squared, or e to the negative r squared, which is what we do in chapter 5.3. We kind of that's exactly what we expand upon in our homework. And then the final step, which was pretty easy to understand, which was u substitution. So we just literally u sub the whole entire thing out. And so, yeah, to the r squared, and then the dr, which is, you take the r, you make sure to take r dr, and you take it out with the negative 2 as the basically the derivative of r and the derivative of u. And then we take the u's, so u times 0 is 0, and then u times infinity is negative infinity. So obviously, because negative infinity squared will be negative infinity. So that will create a different part of our secondary integral here. And then that becomes this u substitution. And then when we expand upon it as we integrate it, we just keep it back to negative 1/2 e to the u, and then we put it in. We can put it onto the variables of negative infinity to 0 again, just back onto the what is it called, back onto the, I guess, oh my gosh, the domains of negative infinity to 0. And then we'll do the simple subtraction of those two quantities. So negative 1/2 e to the negative infinity is 0, and negative 1/2 e to the 0 is negative 1/2. So 0 minus minus 1/2 is going to be positive 1/2. So literally it's just going to be 0 plus 1/2. The integral of that over 2 pi and 0. So the integral of 1/2 is literally just, it's a constant, so it's going to become 1/2 to the variable theta. And then when we plug in 2 pi and 0, we get 1/2 times 2 pi minus 1/2 times 0, which is just pi. And then the cool thing about the whole thing that I found cool in the end is that since the entire thing was squared initially, we have to square root it. So when we square root the whole thing, or what our answer was, we get square root of pi, which is exactly what we started with. So I thought this was kind of very ingenious, and it took me a minute to kind of understand that, because I was like, okay, well, I feel like really the only thing that I could understand everything aside from the beginning, because I was like, how did we convert a single integral into a double integral? But just because I watched all those different videos and kind of tried to wrap my head around it, I was able to understand it. It took a couple hours of searching through videos and trying to find like different clips and stuff, and I kept having to like scrub through and try to find why it was being done. But I found that specific video after going through a couple and realized, okay, this is the concept. And I had to kind of look through the Wikipedia page too to kind of see what theorems were being used. And of course, all it said was Fubini's theorem and polar coordinates. And I mean, those are both mentioned in chapter 5.3, but it doesn't exactly talk about Gauss's theorem. I mean, I didn't look through it further enough to really understand that, but I kept trying to find different things, and I was like, okay, so like how can we understand it? And so I just, I used the Wikipedia page, and then I went back and tried to look at all the YouTube videos until I found an exact explanation. And even then, all it really told me was it was just a trick. So it was the idea was it was a trick it seems like it's a trick based on Fubini's theorem, which makes sense, but also kind of doesn't. I feel like it's almost like the chicken and the egg concept in math, where you're kind of like, okay, so how did we come up with the idea of multiplying both sides of an equation by this? And there's not really like a necessarily set thing of who did it. It was really just, that is a thing that someone came up with, and that's kind of why we're able to solve algebra from more easily today, or something like that. That's kind of the way I see it. So, yeah. But that is how I came to the conclusion, was by mainly just watching YouTube videos and kind of reading through forums to see if I could find any explanations, and they weren't really helpful. It was really just YouTube videos that really gave me the chunk of what I needed to know to understand this entire concept. Wikipedia helped as well. It gave me a lot of the cues and the leads of where to find all the information on it. Like, I had a general idea of what the formula looked like and how it was solved. And I kind of just looked at the pieces, and I was like, okay, can I find different videos on YouTube to solve it? And that's what I did. That was my process. Now, the next thing I wanted to talk about was how can I relate this to real life? Well, let's see. So really, I first thought about the Gaussian integral and how it related to my career of electronics, because I've been studying electronics for a couple of years now. When I was first studying in electronics, I vaguely remember Gauss's law, and it was for just studying the complexities of circuitry and components, and we were just kind of like, okay, what was Gauss's law for? And it was really, we never really touched upon it that far. We just kind of had a basic idea of it. But the idea of Gauss's law basically is the flux of an electric field any closed surface is equal to the net charge enclosed divided by the permittivity of free space. So that becomes this formula. And this is really like a very different kind of Gauss's law, because we didn't exactly expand upon it this far in my other classes that I did this, because I'm not fully into electrical engineering yet, which is what I'm studying. But this is basically just the general idea. And what you would do with this formula is you would take a surface, right? And it would have, a charge on it. And the charge would have a capacitance of some kind. Or not a capacitance, but a charge. And so what you would do is you would take the formula. So you'd multiply, this is what the Q and C, the free space, the charge in free space is equal to 2.0 in this one, for example. And you would divide that by the flux. Or sorry, by the free space. So it's the charged closed surface, the electric field over the free space, the permittivity of free space. And with that formula, you would be able to get specific answers for the amount of charge or the flux that would exist. But you could use this example. It's basically an integral. The entire thing is a formula that is based off of an integral. And this is just obviously one example of how this formula is used. But I wanted to, because there's a bunch of different ways that this formula is also used. It's also, according to what I saw, it was also in what I found online. It's also in other forms of math, such as statistics. But the main thing that I saw was it was in engineering. So specifically for this, for electromagnetism and physics. But yeah, this formula, my entire point is that this formula is derived from Gauss's integral. So I think that, this is kind of pretty interesting. After I read about that whole debacle, just kind of reading through a few textbooks on the formula and stuff, and realizing what this is for, and how you could basically it would be used for, and the surfaces that you would be measuring would be in like 3D space, or they would be like spheres and things, and it would be the exact same kind of thing that we were doing with this formula now, is we're measuring an amount of volume, we're measuring the surface area, the volume, or whatever of a free space in 3D. And so that's what this integral is for, basically over infinity. Obviously, it's over an infinite space, so it's a little different, but because of this formula, we were able to derive equations like this for, many different things. And now knowing all of that, I think I'm definitely, I have a little bit more confidence actually with approaching these formulas now. So I think, as I go on through my engineering classes and stuff, I'm definitely going to have a little bit more fun with all these concepts, because I actually understand overall how we derived, or how we integrated the entire formula, or how we integrated the entire integral, and then use that to derive into completely different formulas that we can use in a lot of everyday things that we do. So, yeah. So I wanted to elaborate on one more thing. I kind of realized that in physics, rather than for electronics, there was two different formulas that Gauss made. So actually, the integral that Gauss had, I'm trying to find if it was used for electronics, but it seemed like this is another dead end that I realize. And so I'm kind of filming this in the second part, because I couldn't exactly figure out how to prove that was related to the Gauss theorem. So I kind of expanded on a little more and read through and tried to see if there was anything else that formula was used for that was in the realm of electronics. So I found an example of how the equation was used in wave packets. So a wave packet is basically used to calculate the dissipation of waves in a space over time, right? So like the waves are condensed and then they slowly spread out, and then they condense again and they spread out. There's basically when they calculate the distances between these spaces and the way that they're shaped, they use Gaussian integral to calculate it, and formulas based on the Gaussian integral as well to calculate it. So that's another thing that I will expand on, is used in the realm of, I guess, electronics and telecommunications, using the Gaussian integral. Since we can predict how waves scatter in space, with this formula, we can find ways to shape them to our liking when creating and transmitting signals over distances, which is what the theorem seems to be used to simulate. And then I'm also going to include a little PDF that I read from Harvard that shows how the waves can be used to make simple notes based on their shapes, which are analyzed by that integral that we just discussed as well. So that is kind of another thing that I found was basically just using the concepts of wave packets, simulations. So yeah, I would say it was basically everything in Gauss's influence of electronics had his integrals, and used not only for the world of electronics and electromagnetism, but also this formula in itself. This integral was also used in wave packet simulations. Of course, it's also used in predictions for specific statistical analysis, as well as physics, like I think not fluid simulations, but particle simulations, like where predictability and things, such as in the realm of quantum mechanics. So I think all of that is pretty neat, and it's definitely, there are things in this that I will be touching on later in my career as I go through engineering. So yeah, that is my overall expansion of this. Sorry, I had to add this at the last minute because I couldn't exactly figure it out until later, but I figured it out. So it's kind of cool to see all these different things that can be done with this integral. I'm very happy that I learned quite a bit more about this integral than I didn't know before. I think it's definitely going to help later with my engineering career. Thank you.